Alright, homies. I'm trying to pick the hardest problem in here to solve. I think I'll do this one here. It says a billiards player, this is number 9, it says billiards player wants to shoot the 0.1 kilogram 8 ball into the side pocket. To win the game without scratching, she performs a draw shot, causing the 0.16 kilogram cue ball to travel backward with a velocity of negative 0.07. That's redundant because it says backward and the velocity given is negative. We just mean it's the other direction. After striking the 8 ball. If the cue ball traveled towards the 8 ball at an initial speed of 0.35 meters per second, how fast the 8 ball traveling when it enters the pocket? Okay, so if I were trying to memorize an equation to solve this problem, I wouldn't be able to do it. If I were just looking at the words, I wouldn't be able to do it. I think I would need to be very organized about it. So I would use a T-chart. This is how I'd recommend doing these kinds of conservation of momentum type problems. So if you set up a T-chart, right? Here, I'll make a new page for you. And you got your beautiful T-chart. And then I would draw just a diagram, and I wouldn't waste time drawing beautiful objects. I just make them all boxes. This is supposed to be the cue ball, and this is supposed to be the 8 ball before the collision. And this is only after reading the question several times that I'm able to figure this out, right? So before the collision, the 8 ball wasn't moving, the cue ball was moving. And then after the collision, in theory, I want the 8 ball to be moving towards the pocket. That would be to the right, I'm guessing. But the cue ball, you absolutely want the cue ball to move back to you, because if it goes in the pocket, you lose. Okay, and maybe the pocket's like over here is the pocket. I'll just write P for pocket over here in this section. So that's where the pocket is. And you don't want the cue ball to go anywhere near that. Okay? And that's just a basic picture that I would draw to start a diagram, if you will. Okay? So over here, I'll kind of label what it is I'm doing. Whoops. I go back. There we go. Whoops. How do I zoom in? I think I go there. Oh, that's how I do it. All right. So that part I would call a diagram. Okay? And then next, oh, I get it. Whoops, I don't want to do that. Okay, there we go. And then I'll move this guy over here. All right, so that was a diagram. Now I'm going to do a vector diagram. Okay? So I'll show that right here. All right, vector diagram. So vector diagram. And this is essential. If you do good vector diagrams, these problems are easy. So the only object moving before the collision is the cue ball. Thus, the cue ball is the only object that has any momentum. So the cue ball is moving to the right, therefore its momentum is to the right. I'll use the symbol P for momentum, and I'll write P with a little q at the bottom. Okay? And then if that's the only object moving, then that is the same as your total momentum. That is your total momentum. So I'm going to make my total momentum vector look different. I'm going to make it look big and fat, because that's the total momentum, but it's the same length, same direction, right? And so that's my total momentum before the collision. All right. After the collision, I have the 8 ball moving to the right, the cue ball moving to the left, and these have to equal the same total, right? So I'm just going to copy the same total momentum vector, right? P total. and I'm going to move it. Whoa, I don't want to move the whole thing. No, that's not what I wanted to do. Maybe I'll try that again. So I'll try that all over again. I'll just draw it over here. How's that? So here's my total momentum vector. It's the same length and same direction as it was before. Okay? There's my total momentum. The difference now is my 8 balls momentum and my cue balls momentum together have to add to that one. The only way that's possible is if the 8 balls momentum is longer. Now this is tricky, but if you drew a cue balls momentum longer, it won't work. Okay? So it doesn't matter the order you draw them, but I'll draw my 8 ball. That momentum has to be longer than the total. And then my cue ball has to be a shorter momentum, less momentum in the other direction. And these two black vectors are adding to that same total momentum. And this is only true if the net force, external force, is 0. So, right, if the sum of external forces acting on our system is 0. That means, for example, that weight and normal can exist, but they have to add to 0. Okay? Friction can't really be there. Otherwise, it's going to mess up our problem. It's going to cause a net force, which causes an impulse on our system, which means the total momentum has to change due to that impulse. That's the impulse change in momentum theorem. Okay? So now I just got to find out the lengths of my vectors. Okay? And this really is no big deal. Over here, the cue ball's momentum should be like, I don't know, the mass, which is 0.16, that's kilograms, times the speed, 0.35 meters per second, right? That means the cue ball's momentum, if I multiply those numbers, I should get 0.056 kilograms meters per second. And that means the total momentum will be the same. So again, I'm just trying to figure out the lengths of my vectors. This one, for example, is 0.056. Okay? That means this one here is 0.056 as well. Right? And then we're given information to find the cue ball's momentum after the collision. So the cue ball's momentum after the collision is going to be its mass times its speed after the collision, 0.07 meters a second, right? And that means 0.0112, 0.0112, and that would be kilograms meters per second. And did I mention this is the hardest problem on the worksheet? This is easily the hardest problem on the worksheet. All right? And then, so if I label that vector, that means this one's 0.0112, right? Well, the 8 ball's momentum, if I just add these two momentums, right? Now I'm not adding them as vectors anymore. If I just look at the lengths, this vector has a length of 0.056. This vector has a length of 0.0112. Okay? I just add those two lengths together. So I'm just treating the vectors. I'm just dealing with the lengths of the vectors. I'm dealing with the magnitudes. So you can see that the length of the 8 balls momentum, that length has to be this length and this length added. Okay? So I'll say that again. The length of my 8 ball momentum, this length, has to be my total momentum's length plus my cue ball's momentum length. Okay? That's just looking at my momentum diagram to figure that out. So the length of my 8 balls momentum, so here I'm just dealing with magnitudes. I'm not worried about directions. I'm just worried about magnitudes of vectors. And I'm just finding all the magnitudes. So again, the 8 ball's momentum vector is 0.056. Cue ball's momentum is 0.0112. Okay? So the 8 ball should have a momentum of, and those are both measured in kilograms meter per second. So what's that going to be? 8 ball's momentum 0.0672. And that's kilograms meters per second. Okay? So the 8 ball has a length, the momentum has a length of 0.0672. Right? Okay. Now let's see what we got. So we got next. Well, if I want to find the speed of the 8 ball, right? Because that's what we don't know. That's probably what we're looking for. So if I know the momentum of the 8 ball, and momentum is mass times velocity, right? Momentum vector is mass times velocity, right? Well, I know my velocity vector and my momentum vector are in the same direction. So I can just deal with the magnitudes now, because I know my velocity of the 8 ball is going to be to the right in the end of after the collision. My 8 ball has to be moving to the right. Therefore, its velocity has to be to the right. So I can just deal with magnitudes. So the velocity magnitude is going to be the momentum magnitude divided by the mass. So now I'm ignoring vectors and just worried about the magnitude of the velocity vector, otherwise known as the speed. And the momentum was 0.0672 kilograms meter per second divided by the mass, which is, what is that mass? 0.16 kilograms. You'll notice that the kilograms cancels, right? Divides into itself to make 1. And this will give you 0.0672 divided by 0.16, which is 0.42. Okay? And 0.42 meters per second. So that's the speed that the 8 ball flies into the pocket to the right. And we already knew it was going to be to the right because the momentum of the 8 ball is to the right and the velocity must be in the same direction. So that's sort of how you calculate whatever you're looking for. That's how you figure out what you're looking for in a simple way for conservation and momentum type problems. You make a T-chart. On the left side of the T-chart, you do a diagram before the collision. Then on the right side, you do a diagram after the collision. Then I made a vector diagram before the collision. I might have to add vectors head to tail to find my total momentum before the collision. In this case, it was simple because I just had one vector before the collision. So the total momentum was the same as that vector. And then you do the same after the collision. You basically do a vector sum diagram, but now it's a momentum sum diagram for after the collision. And then I deal with the lengths of the vectors separately. I don't worry about direction. I worry about the length because I already have the direction drawn in my vector diagram. So I sort of deal with directions separate from magnitudes. That just makes it easier for me. So the diagram is a critical element. The vector sum diagrams are a critical element. And then looking at the magnitudes of each vector and finding the ones you don't know. Doing that successfully is a critical element. And then usually there's something you're missing. If you're missing a velocity, you're looking for a velocity and you know the momentum of that object, well, by definition, you just have to divide by the mass to figure out the velocity if you know the momentum. Or if you know the velocity, you would just multiply the velocity by the mass to get the momentum. Okay? So I figured out that the 8 ball would go into the pocket at a speed of about almost half a meter per second, 0.42 meters per second. And yeah, I hope this helps. This is the hardest problem on the worksheet. Why don't you start with the first 6 problems? We'll try to whiteboard those tomorrow. Have a good day.